Woo. Thank you very much. My name is Malcolm. If the more observant will notice, I'm from Klarna. I'm a very somewhat popular Swedish company. So this talk is about NoDB. Klarna has not gotten into the space industry. This title actually comes from a conversation some friends had where the semantics of NoDB would actually make a lot of sense if you were traveling in spaceships going at light speed and had a lot of latency between them. And I did a cardinal sin and changed much of my slides this morning, so sorry. And it's after lunch, so I get kind of sleepy after I eat, so I might end early, just so you know. So I work for Klarna. We're a Swedish company. We handle e-commerce payments. We're through invoice. We are heavy users of Erlang, and my role mostly was on the second generation purchase taking system, which is meant to be highly available, multiple data centers, all that sort of stuff. They're already working on the third generation, so what I'm saying now is already obsolete. But the last 2 years have been a pretty good experience, learned a lot, and this new system is going from a monolith to more of a broken up distributed setup with lots of nodes that can be killed off very easily and come back without disrupting service for anyone. And one of the components that we built for that is called NoDB, which used to synchronize data between the multiple systems. So it's a database in a very loose sense of the word, where it's actually an overlay for multiple systems all storing their own data, and it's key value based, and it replicates data between those systems, making sure that each portion has the latest version of the data there. It favors write availability, since we're across multiple systems with different SLAs. If one system is down, you want to make sure you can always write to the other system. And that means you don't want to be synchronizing with them on the database transfers or anything like that. So you prefer writing over consistency. It allows for large latencies between a write happening and it making together a system. In practice, it's only in the orders of hundreds of milliseconds for database to get around. But in theory, you could have days or weeks, or in theory, infinite latencies. So what is eventual consistency? It's very popular. There's tons of talks about it. If you have a lot of questions, Chris John Michael over here has done multiple talks about eventual consistency. This is the definition I pulled from some ACM article where guarantees that if no new updates are made to the object, eventually all accesses will return the last updated value. So it's kind of a difficult concept at first, where if you do a put on one part of your system and then do a get, you might not read what you just put. You could even travel backwards in time, where you read a value that was there before you did the put. It's confusing a lot, I would say, at first. And it means you have to write your code in a very robust way where you don't actually care about what time is for your system. Two very popular ones are React and Cassandra. React is what we use, and what I talk about will all be built on top of React. Cassandra has some nice features, but it didn't really suit our use case here, and it has a different look on what eventual consistency is and the properties for it. And so like I said, you don't have a lot of control over what you will read versus a write. So why would anyone want this sort of thing? If you read the Hyperdex blog, basically every third blog post is how we're a bunch of idiots for using eventual consistency. But it actually has some really nice features that are very simple to wrap your head around. It might not be simple to write code for it, but at least it's very easy to reason about. One thing is scalability. So for React, if you are running out of CPU, RAM, or disk space, you add more nodes, and all of a sudden you have more of this across all of your machines. So you can scale out in that way. And it roughly comes out to be about linear. Availability, so for React and the NoDB model, favors write availability. So if some portion of your network is down, or some machines are down, or anything like that, as long as you can talk to some group of the machines, you can always write. You can control that, so even if you talk to only one node, and your whole cluster of 9 or whatever is down, you can still write. So that means you, if always being able to put data into your database is important, you can set it up so that always happens. Geolocality, if you are a company that is across continents, you often don't want data to be owned by someone by a data center in Asia when your clients are in the US, or if they're moving around a lot. So with a masterless setup where nobody owns the data and it is across all these setups, you can always write to the data center closest to you, and your write will be accepted. So you get good latency in that case relative to possibly locking across a continent or locking a row, something like that. And finally, this is sort of a new thing that we have coming out in our system, but it turns out eventual consistency is really nice if you want to cache database reads. You already have written code that doesn't require the latest bit of data to be there. So when you cache, you don't have to do anything particularly fancy about it. You just expire it over some time, and then you read the next one from the database when you're ready. But a put, you already don't expect it to be able to read what you put back. So it simplifies that whole layer and makes a lot of cache bugs that people run into go away. And some examples of eventually consistent systems. DNS is probably the example of the oldest and global eventually consistent system. When you update an IP for a DNS record, it takes time to propagate around. That latency is unknown. You can take from days to minutes. Amazon, of course. I don't know what their current setup looks like, but they are famous for writing the Dynamo paper, which is what React and Cassandra are based off of, and really sort of creating the eventually consistent public movement, I would say, in a lot of ways. Their goal there was to be always on, so when they're not working, they're losing money. That's a very similar problem to what Klarna has, where if we are down, we lose money. And Amazon solved this by making a masterless setup where it doesn't matter who you're talking to or whether they can talk to the rest of the network. You can always put values there. And then they push it back to the application layer to resolve any mismatches in those values. So if you add an element twice, you can resolve that. Well, if you add an element once and it shows up as twice because you had some sort of partition there, you can resolve that on the application code. And financial transactions are oftentimes, I think a lot of people think that there's some sort of ACID transaction, but I guess they don't really have them in Sweden. But if you've ever written a check in the US, you write how much money you want to give to someone on a piece of paper, and you hand it to someone, and then you walk away. And then like 3 weeks later, your money disappears. So that's not a lock that's being held for 3 weeks. An example of where eventually consistency I think will at least play a big part or shine is the Interplanetary Internet, which is actually, sounds quite futuristic, but has been used already. The basic premise here is you have a network where there are massive latencies for any operation going across a large distance. When I looked it up, the latency for the one-way trip time for a light between US and Mars was about 3 minutes. So huge latencies. You can't do an ACID transaction when it takes 6 minutes round time just to know if you've actually successfully taken a lockout. You also have a setup where you're going to lose a lot of packets. The ordering is not going to be controlled very well. And your error rate is going to be very high. Luckily, the error rate is a big problem for our networks, but the idea of having to hold on to data and then the ordering not getting to your other system in the order that you wrote it is an issue that we have. And The solution for the interplanetary internet is this setup called delay-tolerant networks, where you have many components that all store their data locally until they know they can hit a system, because they expect most systems to not be available all the time. And once the system comes back online, they push it out again. And at the application layer, you have to be aware of the fact that you're going to get possibly the same data multiple times and not in the order you expect. So it looks a lot like an eventually consistent system, and the data that you send through a system like that also has to be workable with as well. Another example of very consistency, for those who don't know, this is the Borg from Star Trek, which are a cyborg life form that assimilates other groups and all around takes over worlds and destroys them. They are a hive mentality where they can communicate with each other quickly, instantaneously. They also assimilate the knowledge of other civilizations, pull it into their collective consciousness, and modify what they know based on that. The movie First Contact is a time travel movie where they go from the future into the past. And during this movie, the knowledge that some of the Borg come back makes it to the, is transmitted out to the rest of the collective, and it's incorporated into the collective just fine. So the Borg can clearly handle out-of-order data trivially. Time is not a big component in how their database system works. They internally, a cube could be considered transactional, where each individual component inside of it can happen instantaneously and with a consensus. But across their spaceships, they have, you can have blackouts in time and resequencing and reordering. This is Hugh, the first Borg to get an individual identity of his own, which ended up destroying his whole collective, but that's a different story. The interesting thing about him is he was cut off from the rest of the collective for some period of time, and he learned new things while he was cut off. Once he was put back into the wild, all of the knowledge he accumulated was merged back into the rest of the system. So this is just like a network partition happening, where you have this one lone guy cut off, and when he comes back, all of the knowledge he has is reincorporated into the system. All right, so with all of that, what is this really? And NoDB is more of a model than anything else. We have two implementations of it right now, one for different types of system that we work on. So it's not like one unique piece of code, and it's not one product you can really put into a code base, although we're working on bringing it together. And like I said, the main goal is to take separate components of a system and allow them to replicate the data between them so they each have the same database and look the same. It works across our transactional store, and it works across our eventually consistent store. Of course, the fine print here is that you are eventually consistent between those stores. So even though you have a transaction inside a transactional store, the actual movement of data will not show up until it makes it across the application. So you can't make any assumptions about that. And NoDB itself doesn't actually store any data. It is just a way to look at your system and to replicate data around. On one system, it doesn't even have an API all of its own. You use the transactional API. And on the other system, it does have an API that looks like a key value store. It replicates React's API quite a bit. So it's not even a consistent API for you to think about. And the main properties allows out-of-order replication of data, doesn't consider time, or at least wall clock time in a meaningful way. And it is very nice for the use case that we have right now, which is going from a monolith to more of an SOA architecture. So in general, I would say components should own all of their data. But when you're breaking up this big piece into a bunch of smaller pieces, you often need this transitional step where everyone can see all the same data and modify it, and it goes around to all the other systems. And then once you've made it to the point where you've actually pulled a lot of the code out, you can start making that data actually owned by the other components. And at which point you can start turning replication off, and they can have their own data model, their own whatever. But as an in-between step, this has been very handy. And a very useful component in making the breakup go much smoother, I would say. Because of the replication of data, you can have the same component running on both systems for a while until you trust it on the new system. And they will both sort of function mostly just fine as long as they understand the semantics of their replication. And then once you know this new system is good, you can just flip off the component on the other one, and you're ready to go. The main component of NoDB is a vector clock. This is a pretty obvious diagram, as long as I don't explain it to you, of vector clocks in action. The basic premise here is just that when somebody in a distributed system updates the value, that actor puts himself into the vector clock and increments some value. And then once it makes it around the system, everyone can say, hey, is this new value in line with what I know already? Or did somebody change it at the same time that I changed it? And in the first case, it's fine. You just take that new value because you know it's the successor to your value. Or you might actually have a value in the future as well, so you know you can throw that value out because any value that you have already has that value incorporated into it. In the second case, where two people have modified the piece of data at the same time, you know you have to do some resolution on it. And you will get 2 copies of that data, and then you do something to it to make it 1 version again. This is pretty standard for using something like React. They're building the ability to handle siblings into it directly if you model your data a certain way. That's before we started working on NoDB. So in NoDB, every piece of data that you replicate has to have a function that takes 2 values and gives you 1, or it completely fails. And that's very important because since two components can update the same value twice, you never want to lose writes. So for the case where 2 values are updated, you always want the ability to compose these values together. So since both our sides are in Erlang, this is very easy for us because you just implement a resolver library and you put it on both sides. For a case where you have something like NoDB but different languages on the other side, you have to make sure you implement these resolvers the same way. And NoDB is kind of the obvious first use case when you learn about vector clocks. You have this thing that tells you the rough partial ordering of events, and you just add a piece of data to it, because what else are you going to do? So the implementation NoDB, like I said, it's in Erlang. We have 2 systems. One is the one that I mostly work on, which uses React as its data store. This is a distributed purchase-taking system where we have a whole bunch of nodes. Currently, we have 2 React clusters, one in and 2 databases, one in each, or data centers, one in each data center. And with NoDB, we can replicate across data centers, and even the other components, doesn't matter where they are either, since it looks all the same. Manesia is the system of record, so anytime you populate one of the other systems, the Manesia system, which is the legacy one, is where you pull that data from. We use RabbitMQ as the transport. So it's a pretty simple queue setup where we just replicate in sort of a connected graph, since we don't have a lot of systems at the moment, in queues. And we want it to be very simple, very understandable. So everyone sort of listens on the same group of RabbitMQ brokers, the same cluster, and pump data into it, and everyone sucks it out and pulls it into their local systems. We support RealTime Replication, which is the way it functions most of the time, where you're just doing operations, and as they happen, they get sent out to everyone else. There's no sort of clever. The scale we're going at has no sort of clever buffering or anything like that. You can do each operation as it comes. We also support manual exports. That is always from the Manesia system of record, where you say, I've had some downtime for whatever reason, or I know something happened, a bug happened. I need to replicate the last day's worth of operations out. So the Manesia side, we have a layer on top of Manesia that has a transaction log on it. And code can listen in real time to the transactions. And they can also walk over the history of the transactions up to like 7 days in the past, something like that. So the real-time replication works by listening in the transaction log and then takes the key value operations, pulls out which ones it cares about, packs them up into a NoDB operation message, and then sends that through Rabbit. The reason Manesia is the system of record for this is because we can iterate tables in all the keys in a very easily in it. You just do a dirty operation where you go through and get the next value and continue and push it out. That's much harder in React at the moment. It's possible, but it is not a use case that it is meant to support. And the ability to replay the transaction log has come in extremely handy several times. We've had a bug or two in our integration with RabbitMQ on our side where we lost some messages due to a network partition. And while we had to fix that bug, of course, we also had to make sure that any data we lost actually made it there. So you just say, let's rerun the last whenever this event happened. The vector clocks, so this is an old Manesia table that we have. So it's a lot of legacy there, about 10 years or so. And you can't just take every single piece of data you want to replicate and then add, modify the value in Manesia and add a vector clock to it. So we use a shadow table where we have a lookup for how each table maps to a vector clock table, and then anytime you do an operation, you go and you pull out and you do a read on both of these. It turns out to not be that expensive for us, but it would be nice if we could have them all together, but too much effort there. The React side, so the React side actually, a person doesn't, or a developer doesn't realize they're actually interacting with React. They know their semantics match React, but they don't actually know what's behind that. They use a direct NoDB API. And it basically just has your put, get, delete options. When you do any of these options, the API makes the operation on React happen, and at the same time pushes it for replication. Any importers are just listening on Rabbit and then pushing in to React, and they have a flag that says don't replicate this. We have to handle the case where Rabbit is down for whatever reason, either network partition or maintenance on it. So we locally queue things because we can't do a manual export and we don't have a transaction log on these machines. We just build up a little local queue on with a disk log, and then once those come back, shoot it off again. And in this case, we had more control of the data model since it's all brand new, and the vector clock is stored with the data rather than as a separate, which is, if you think about it, it's the only way you really can do this, because if you stored it as separate keys, you could not be confident that when you read the value and you read the key, you're actually getting values that were consistent with each other, given the model of React. So what happens when you update some data? First, you have to get your previous data. This includes the vector clock, because you want to know what you're modifying, and you have to make sure that the modification you're adding to it works. For the most part, data in NoDB has to look like a lattice, where you only go one direction on it. You can never modify a value going the opposite direction, because you have no way of knowing if resolving that in the future. So after you get your data, you bump the vector clock. So you say, this is who I am. I'm modifying this value. Let me increment my entry in the vector clock by 1. Then you write both of those back and you replicate it. And for the Amnesia system, we actually have this nasty little piece of code where anytime you do a transaction or a write operation, it behind your back looks at that and sees if this is something that it's going to replicate, and then it sneakily pulls the vector clock out on its own and then modifies it and pushed it back. We actually had an interesting bug one time where somebody realized that this was slower than they expected, so they changed the read of the vector clock to a dirty read amnesia, and all of a sudden you're getting inconsistent values because you're dirtily reading a value that somebody else has either not updated or in the middle of updating, or they don't know that the transaction layer doesn't know they need to serialize on this. So that's fun. And on Amnesia, since we have transactions, we can do any resolution of siblings on write time. So you go and you get your data, and you look at your data you're going to put in. You make sure that the vector clocks make sense and resolve it if they don't, and then you write. Whereas on the React side, we do it in the opposite way, where we always just push data into React, doing a write, and then on read, you resolve any siblings, and we will fix those siblings on an update. Otherwise, you'll just keep on resolving it as you do reads. So the retrospective on this is everybody hates using this, actually. It's hard. It tells you when you're wrong, and people don't like to be wrong. And that's why they're wrong when they hate it, because people oftentimes want to do things with your system that they shouldn't do, and they don't realize how wrong they are because there's nobody to tell them that they are. And luckily, while it feels like a prison sometimes, the semantics we have actually inform you when this is going on. So it complains, and then people have to come to us and wonder why we're such jerks making them use it. Out-of-order events are ridiculously hard to do, especially if you're used to transactional store. Even if you think you have it down, just like some weird edge case comes up where like you just thought something would be there, even though you knew you shouldn't have, but your code expected it. Or you're multiple layers of abstraction away from two things, and you didn't realize something else depended on certain things being a certain way. So we hit some bugs with that every now and then, but it's not so bad. They're pretty easy to solve usually. So the semantics of NoDB are so simple. They're hard to work with, but they're simple they're simple in general. So once you know what's wrong, you can fix it. And being able to replay writes is great. We have several times saved ourselves from losing a bunch of money because of this. Even on the React side, where we can't iterate tables, we don't have a transaction log, we log a lot of keys out to that, to the disk log, not disk log, to the actual just logger log. And we've had multiple times where we've realized that we've lost something, and we scrape the logs and then just rewrite that little piece of data out, which turns out to be really helpful. And this is actually one of the nice properties of it being databases rather than message queues, because the data is always there. So if you lose something or somebody processes a piece of data wrong or anything like that, your data is still on the other side, and you can just retransmit it out rather than having to recompute it or something like that, if you can even figure out how to do that. So all of our data is still in the databases all the time, and that makes it really convenient when you've messed up. For future work, we really want to unify the code bases. They were written in haste by one person on each side. Neither of them was me. And there's a lot of things where it's mostly doing the same thing, but not quite. And we also didn't really understand what things should have looked like at the time. We just needed some replication working because it's how we could get the system going. So there's some technical debt there that we are working on cleaning up. For our case, RabbitMQ doesn't actually add much because we really need guaranteed delivery. And we know it's a certain set of people that we're going to pass data between. And so if something goes wrong, like your RabbitMQ's partition or anything like that, or some way in which you lose data, for our use case, we always want to get the acknowledgement back that the data has been pushed into the database on the other side. So for us, more of a direct communication is what we're after, and we're moving slowly into that area where we'd have some sort of service discovery system, and then those, you just say, I want to replicate this type of data, tell me who to talk to, and there you go. The other thing we want to do is make this easier for non-Erlang systems. We have one other component that's, so we have two major components and then another component that's pulling this data off. And we're getting a possibly fourth consumer in the near future. And right now, our data is actually just term to binary. And they want to write their component in Ruby. So there's a little problem there. We're probably going to go with just something like JSON or something like that for the actual wire format. And one idea we have is to have Postgres support, where we have other components coming up that are going to be in a real relational database. And it's unclear how to actually fit this into the model, but it'd be really nice to give them the chance to put their data into a database they like, and then pull that data out of the legacy system as needed. But again, that has a lot of I just don't know enough about Postgres, and we don't know enough about Postgres to do that yet. So, any questions?
Well, thank you, Malcolm. And as he promised, he finished early, so we have plenty of room for questions.
So I didn't quite get how you use RabbitMQ. As I understand, NoDB is on the top, React is on the bottom. Where is Rabbit?
So you have NoDB is on the very top, and then you have like React and Manesia, and NoDB is using RabbitMQ to push data between those two components. So anyone that wants to listen in on data changes or push new data changes in will write to a RabbitMQ.
Right. And my other question is, how many React clusters do you use?
Right now we have 2 clusters, each with 9 machines in them. So far this model has scaled pretty well for us. We have 1 cluster in each data center. And because latency isn't an issue for this, we should be able to add, like one in the States or UK or something like that if we ever got the opportunity.
Right, and when a piece of data comes into NoDB and you have to write it, how do you decide which React cluster to put it into?
Since we're using vector clocks, and you can tell when you have a piece of data whether this is new for you or not, we actually just write it to everyone. So right now it's inefficient in the sense that it's a fully connected graph, but it's not a problem in practice because everyone can tell whether it's worth writing for them or not. And the number of database operations for us isn't so high that that's a performance problem right now.
Right. But I mean, in the beginning you said that one of the motivations was that if you have data centers in different continents, then you don't have to send your data.
Well, so I'm sorry, I phrased that poorly then. The nice thing is that you don't have to worry about the latency for data getting there, but you can send all your data everywhere.
Right.
So eventually consistency in general is nice in the sense that data can travel all around the world, and it doesn't necessarily matter how long it takes to get there, but you know that there's no necessary owner of it where you have to consult with that person, with that server, whether it's okay for you to write that value or not.
Right. And do you have multi-data center replication between the React nodes?
No,
we're
we're just using NoDB for that.
Right. Yeah, because you write.
Yeah, so we
everywhere
already had it
so
there. We know how it works, so we figured it wasn't worth the extra duplication in functionality.
You said you don't delete any data. How long do you expect to keep up with new data?
So our data is usually pretty small in of itself. We have compression turned on for everything going into the database. So the growth of the data hasn't been too big an issue for us. On top of that, because at least on the React side, we can just add more nodes to get more disk space. Not too concerned about it in that regard. And we are also only replicating a subset of all the data on these two systems, so the ones that they really need to operate on both sides. So the amount of data going between the systems is actually not so huge.
Okay, thanks.
Hi, could you tell us a little bit more about the conflict resolution siblings thing? And I think you said that there could be a failure scenario. What would that be? And is it possible, or when is it not possible to do that kind of automatically?
So the failure scenario in all of these is basically call whoever's on call and have them manually fix it. We haven't actually run into that problem yet, but in the end, with anything like this, it's always going to come down to a person. For us, we strive to make most of our data immutable, which means even though you should have a resolution for it, if it is immutable, then you know you never have to resolve any conflicts. Pat Helland has a pretty good talk about this, or paper, I forget which, where he just tries to point out various ways that you can make data immutable just to make your life simpler in a distributed system. We have, for the things that we do resolve, usually you try to make it look like a set, or we have some counters that we use where it's just you always take the highest value. So it really depends on the specific piece of data. If you read the literature on something like CRDTs, if you can fit your data into that, which you should be able to do for most things, then there's generic algorithms in there. We aren't mature enough, I would say, to in the system implementation to have something like CRDTs used, but it's a definite direction we'd like to go in the long run.
You said that first of all, I would like to ask how many transactions do you have, or what kind of data volumes you pass through your systems. On your website, I see something like 70 million transactions per year. And my second question is, how do you deal with data which are, you need to have relationships between data. From what I understood, you have a key value type of setup in your refactoring, or but how do you deal with the relationship of data?
So the second one, for relational data, we don't really have much of any. We might have things that are pointers to other things, so some kind of relation, but for most of the data that we are replicating between them, we basically denormalize it and pack all the data needed inside a particular object, and then other sides might decompress it out to multiple tables, but still keep the data inlined in that way. And the actual transaction volume is not super high. I think we're pushing on real time several like 100 per or 100,000 per 10 seconds, or several hundred per 10 seconds, something like that. So not incredibly large number. For one-off exports, we can, depending on the type of data, we can push something like so like 20, 30,000 updates per second.
Just similar to the earlier question about conflict resolution at the application layer, does that mean, well, you mentioned you had both systems were written in Erlang, so that keeps them consistent, but if you did have, it would constitute a bug, I take it, if two different pieces at the application layer were resolving slightly differently. That would mean that the eventual consistency model becomes unstable and data would bounce around.
Yeah, definitely. Yeah. That'd be a pretty serious bug. Yeah. For something like that, I would try to do like some sort of property-based testing. So you just define your resolvers and the properties around them, and then use something like quick check. Hopefully it exists in all the languages one would use.
Would that affect performance?
I don't think so. So for, depending on what kind of your underlying database is, whether you're resolving on reads or writes, first of all, for the most part, we don't hit siblings, so we're not resolving particularly often. It's a pretty rare occurrence. I think in the Dynamo paper, they hit siblings like 0.0 something percent of the time. So in that sense, performance wouldn't be an issue. And for most pieces of data, the actual resolution functions are pretty trivial. Like you might do a set union That's most languages. That's a pretty fast operation, assuming and the sets are usually pretty small as well, unless you're really pounding a piece of data.
Yeah, thanks.
Anything else? Well, let's thank Malcolm.
Thank you.